Today we will do some graphs in Haskell. We will start from graph definition and then we'll write some simple functions which helpful to work with graphs. And also we will write simple DFS, BFS, and find all paths and find minimal paths function. At first, let's define our graph edge. We will start from undirected graph. This means that our edges have no direction, and we can represent our edge with undirected edge data types, which take some type on input and produce a pair. We'll construct this with UE constructor, and also let's driving show. Okay. The next thing which will be helpful, I think this is a simple constructor function which takes some A and B and build our edge type. Okay. And now, because we have undirected edge, let's make an instance of EQ for our edge type. And we need to define equality function here. We will unpattern match our edges, first and second, and also second edge. And how we define our equality? Okay, two edges equal if our corresponding elements of edges equal. This means they equal if A equal A1 and B equal B1. And also they equal if A equal B1 and B equal A1. So because order doesn't matter, we do this in this way. Okay. Let's try to load our model. And it's done. So now let's define a graph itself. So the graph is polymorphic data type with some parameter A, and we will construct it with G constructor, and the graph is just a list of edges. We can represent it in this way. Okay, and let's derive show. Okay, now we can build some graphs. Let's build graph G. We need constructor G here, then we need list, and in this list we need to create edges. We can create it with its constructor. For example, like this. If we have edge from A and B, and also we have edge from B to C and H from A to C, for example. Okay, let's try to reload, and we can see that we construct this graph, simple graph, with our data structure. Now let's write some helpful function. The first function I want to write, this function we'll call Vertices. It will produce a list of vertices which contains in our graph. So we have some graph of A. A must be in equality type class, and we need to produce a list of A's. So let's start with implementation. We need to pattern match our graph, and the next thing we need to, okay, let's use list comprehension here. We can extract from our list our ages, and let's unpattern match it. So every age it's constructed with its constructor, and it has a pair inside. And now we can take this AB and produce a sublist here. So we have this list of ages, of vertices of the ages. And what we need to do, we need to, of course, it will contain duplicate elements, and also it will be a list of lists. We need to remove extra layer with join function, and then we need to remove duplicates, and this we can do with the nub function. Okay, the join function, we need some modules here. Import control monad, I think. Control monad, and import data list, which contain nub function. Okay, let's check the errors. And we're done. So let's check the vertices of our graph G. We can see that we have vertices A, B, and C. So we have no repetitions here. This is all our vertices. The next helpful function I want to write is adjacent function, which shows which vertex is adjacent to some vertex. Okay. Let's start from type signature. We need a quality type class for our class A, type A, and we will take some graph on input and some vertex, and produce a list of adjacent vertices. And let's implement this thing. When pattern match our graph, take our vertex A, and now we need to take every edge of our list of edges, and they need to find opposite vertex of A, opposite to A. in every edge we need to find an opposite to A vertex. If, of course, if our A contains in this edge. Okay, so we will use some helper function for this. I will define it later, but now I just write it here. So this function will take some edge and our vertex, and it will return maybe a result, because the two vertices cannot be connected. And if they connected, they will return the opposite to A vertex. So now let's implement this function. Opposite adjacent. Type signature, it takes some edge of type A and some vertex, and produce maybe of A. And of course we need equality here. Type class. And implementation is look like this. Opposite edge. We take some edge here and pattern match it, and take our vertex x. If A equal to x, then we return just opposite B. If B equal to x, we return just A. And otherwise they return nothing. Okay, and they call this function from here for every edge. Of course we have a list of nothings and maybes here, and they need to remove nothings. They've cut maybes function. Cut maybes. Okay, and in this way we will receive all the adjacent vertices of our vertex, and maybe it will be an empty list. So let's try to recompile. Okay. Okay, I think I forgot here this thing, but also some errors. And the problem is in naming. Okay. Let's reload. Cut maybes. Okay. Cut maybes. Data. We need to import data maybe for this function, and be done. Okay, now we can get adjacent vertices. So let's a little bit. No, let's take adjacent vertices for our graph G and vertex A. Okay, and we can see that we have B and C, and this is our adjacent vertices to A. Okay. Now let's write a function which will tell us is two vertices adjacent or not. So it will take some A, vertex A and vertex B, The type is the same and it will return a boolean. And to check if it works, we just need to of course here we need to take some graph of type A. Here we need to unpattern match this graph to have its list of edges. And now we can check just using a length function. We need to construct some edge for its list. So we construct H from A and B, and we check if this H in our list with a length function. We can check this because our H is we have an implementation with this equality type class. So now let's reload. Of course, here we need to change this thing, and okay. And now we can ask if two vertices adjacent and or not. Okay, you can see that A and B is adjacent in our graph G. But for example, B and C also adjacent, yes, but B and A all adjacent here. Okay, let's take some unexistent vertex, and you can see that there is no such adjacent. Now let's do some function which will check if some sequence of vertices is walk in graph or not. So what is a walk in graph? The walk is if we have some graph and they go from one vertex to another, and they can go only if two vertices is adjacent. So I can go like this: A to C, C to B, B to A, again A to C, B back C to A to C, and so on. So I can go infinitely long. Okay, the only condition which I need to net to go is that two vertices is adjacent. So I will call this function isWalk, and it takes some graph of type A, some list of vertices of type A, and produce a boolean. Also, we need equality. So isWalk. If we have an empty list, I think this is true. Okay. And also, if we have some list which contain only one vertex, then also it is a walk. But what if we have a list that contains more than two vertices and we will unpattern match it. And some graph G. The first condition which we need to check is that this X and Y vertices is adjacent, and we have functions for this. We can check this like this. And also we need to check the tail of this list, okay, for our work. And the tail is start from Y and our XS. Okay, like so, I think. Now we can check works. For example, in our graph G, we can check that A, B, and C, I think, is a work. Yes, but A, B, C, and for example, X is not a work. So we can add some connection here, I think, for X and C. Okay, and we have A, B, and X, for example. And this is not a work because there is no edge between B and X. Now let's check that some sequence of vertices is trail. The trail is a walk without repetition of edges. Okay, this means that I can start build our trail from A, go to C, go to B, but I can go to A from B, but now I can go to from A to C and A to B because these edges are repeated. I can only repeat vertices. So I can start from C, go to A, then go to B, then go to C. But here I again in C and I can't go to A, but I can go to D because I don't use CDH before. So this is a trail. Let's write function which will check this. Okay, is trail. Type signature exactly the same, but implementation is not. Okay, we take some graph, take some list, and first of all, the trail must be a walk, and we need to check this. Okay, they will check this condition, and they will add some constraint here, and constraint. This constraint, we need to eliminate the duplication of edges in our walk. And to write this constraint, we need some helper function. I will call this function connect nearest vertices with undirected edge. And its type signature will be take our list of our trail vertices and produce a list of undirected edges of type A. it will just connect the all neighbor vertices with an edge. So in the simplest case, then they have empty list, and if they have only one element, only one vertex, we can't create an edge because we need two different vertices. But if we have some vertices here, at minimum more than two vertices, then we can at first create an edge between two head vertices, and then we need to add this thing to our recursive call. And in this, we need to take our tail in this argument. So in this way, we will connect all nearest vertices. Let's compile this and look at some example. Okay, is trail. Okay, just will comment this thing. Comment will write true here. Okay, let's take our function and see what it can do. For example, I will give this list of vertices, and you can see that I get the connection from A, B to B and C. And if I give here the A, B, C, and D, I give connection from A to B, B to C, and C to D. So if the number of vertices here is n, then we have n-1 edges to connect them, to get this line of vertices connected with each other. And now we can write our constraint, additional constraint for trail here. The trail is a walk, and also this one constraint, I will write it in this way. Then, if we have all the edges of this checked list of vertices, and the length of all the edges here must be equal to the length of not duplicated edges. Okay, in this way, if this condition holds, I can say that there is no repetition of edges here. And to get all edges in our L list, we need to just connect them with our helper function. Connect nearest. Okay. Okay. And here we can check for our graph G some trail. So we have such graph G here. Let's look at this. And now let's check that is trail G, for example, A, B, and C. you can see that yes, A, B, and C forms a trail. But if I have A, B, C, and B again, this is not a trail because I repeat B, C, H. But now let's check the case if we have some repeated vertex. We need to modify our graph a little bit. We need to here A to B, B to C. We come back to C. Actually, we cannot modify it, I think. If we have some such a way from A to B, from B to C, from no, we need modification. We need to change this here. So if we have from A to X, we can go from A to B, from B to C, from C again to A, and then, so we repeat A here, and then we have go to X. And this way we will have repeated vertices, but no repeated edges. And this condition must be hold, and this is this trail. This is strange. A to B, B to C. And this is really strange because there is no repetition of edges here. Let's check our function. What it produced to us. So AB and B to C, C to A, and A to X. And if I will take the length of it, it takes me 4. But if I take length knob, I think it's this is also 4. So this is hold, and this walk must be hold. Let's check how is walk. Is walk for G-graph. Why this is not a walk? So I check for adjacency of AB, BC, ACA, and AX, and found that our function walk is H doesn't detect this adjacency, because here we have A and X, and here we have X and A. So something wrong with our previous definition, and I need to find this thing. So how to find this? I think the problem inequality, somewhere inequality. So how our is adjacent work? It's just create the pair. So if I create the pair of A and X, and check this pair for equality for reversed pair x and a, I will receive true. Interesting. But our is adjacency returns false. And this is really strange because lm, I think, use a Q-type class. But now let's check this lm of our pair a and x, and they have some list of x and a. This is very, very strange. Oh, guys, sorry. I think the problem that was in these letters. I put some Russian letters here, or maybe C, or maybe A, and maybe X. I don't know. I changed this to English, all in English, and they start to work as expected. So our isTrail function works as expected. Here I can check this. isTrail G. Yes, isTrail, we can see this. And here we have repetition of vertices, but no repetition of edges. So if we add some edge repetition here, we will break our condition, and this is give us false. And now let's check the sequence of vertices for that is a path. The path is trail without a repetition of vertices. Or also we can say that the path is a walk without repetition of vertices also. So, and let's define it. Same type signature. And that first we need to check that is walk, like here we can copy paste it. But here they need another condition. Actually they have exactly the same, but here they need to check our list of vertices for duplicates. If they remove the duplicates, the length must be the same. In this case, this is a path. So let's recompile and check our path. A, B, C, E, and X. This is not a path because we're repeating our A. If I remove A from here, this is also not a path because I think there is some connections in our graph. So we have no connection with C and X. And to make this a path, I need to, I think, to make something like this. If you go from A to B, from B to C, and this is a path, okay. Or if we add X here, this is also a path without repetition of vertices. And now I want to say that the walk, the trail, and the path can be closed or open. This is an additional condition to this to these elements, and it's open if if its start vertex is not equal to end vertex, and its close otherwise is if they are equal. So, for example, a closed path is a cycle, okay, or closed rail is a circuit, okay. So let's implement the open condition at first. If no matter what is a graph, and if we have empty list, this means that this is I think this is true, okay, this is open. And also if we have only one element, it's also true. But what if we have some list here? The condition that we need to check is that our head of our list is not equal to our last element of the list. In this case, this is an open path, rail, or walk. But here also, of course, we need to check that all vertices of our list is presented in our graph. And we can check this by, I think we can pattern match our graph here. And we need to build a set from L1 and from L, and check these sets for equality. Or also, I think I can make this thing without sets, sorry, using difference of the list. I think, let's check, should this work or not. Strange, because I import this here. Let's reload. Let's comment this thing. And now let's try to use this. Why this is not works? I think it's otherwise. Yes, I think I can use it, can check this without sets. Okay, all I need to do is I need to take vertices of G, of my graph G, and subtract the list from them. And now I need to have an empty list. And this will tell me that lists. Sorry. I need to remove all the vertices from my list L. And if at the result I will have some vertices, then this means that our list contains some vertices what not in our graph. And this is break our condition. So I must have empty list all this here. Okay. And now I can check. Open G. Let's look at our graph. Open G. For example, A and B. Yes, A and B is open. But for example, A and Z is not open because Z is not in our graph. I think, of course, it is better to have not bool and maybe bool type here. But for simplicity, I stay this implementation like this. And now I can check, for example, A, B, C. For open, okay? And of course it's true. Okay, A, B, and C. And if I have X here, this is also true. We have all the vertices from this graph. And let's check let's create a close predicate exactly the same as open. But I can say that close equal not open. Okay. So I think I need some parameters here, G and L. So like this. Open, close. Okay, it works. Okay, and in the end of this video, I think we will write a last one function which find all the paths from some node A to some node B. Okay, and this will be the last because video goes too long. I think the DFS, BFS and others we will be writing a video part number 2. Okay, let's start the all paths function. I will call it paths, and type signature is we take some graph of type A with this constraint to equality. When next thing we take a list of already visited vertices. we will implement this recursion, and that's why we need a list of visited vertices. And also we need start point and end point. And at the end we will produce a list of A, a list of all paths. Okay, and the implementation, we take some graph, some list of visited vertices, start point and end point. And if our start point equal to end point, this means that they can return a list of lists with some point A, because this is all possible paths. And otherwise, if our start point not equal to our end point, in this way, okay, we will implement this recursion. That means that we have all the paths function, and we can take all the adjacent to our B vertex vertices, and then they need to remove from these all adjacent vertices the vertices what we have visited. We can do this with this operator with lists. Okay, we have this thing. And now, if we take the all paths for every of these adjacent vertices, we can take these all paths. If we fmap this thing, all our paths function again. Of course, partially apply. We need to initialize it a little bit. Initialize this with our graph G, with our visited vertices, plus our B, and also our start point. So we take this function. Actually, this will be partially applied paths, graph initialize, and so this function from A to list of lists, and every this A in this list. Okay, now what we have? We have all the paths from all the not visited adjacent vertices, and this type is list of lists, and we need to folder this type with list concatenation. Fold the L, and we start with the empty list. So this thing allows us to collect all the paths which goes from the adjacent to B vertex without already visited vertices, because they subtracted here. And the last thing they need to do, they need to fmap this list, we need to add our visited vertices B at this step of definition. So it looks like this. So this implementation is similar to the implementation then we find all the possible paths in a tree, in a binary tree. But in the binary tree, there was only two subtrees, two adjacent vertices. But here we have infinitely many of them, and we must folder them all. Okay. I think we can try to compile this thing. Okay, some problems. Let's try to add some parentheses here. And recompile. Okay, it's done. And now let's look at our graph G and try to find paths from A to C, for example. And we need to, at start point, we need to put our visited list is empty. Of course, I need to pass the chars. And you can see that here we have two ways, from C to A, from A to C, and from A to B and B to C. Okay, I think this is the correct result. Okay, as I said, this implementation is similar to the tree, the find path in tree, but in the trees we don't need this visited list because the trees in definition have no cycles. But in the graph we can have the cycles, and that's why we need to define our visited vertices of every step of our recursive definition. Let's add some paths in our graph to check that this is correct implementation. Okay, I will add some from A to B. And for example, what if I have from B to Z and from Z to C? Okay, this will create a new extra path for us. From B to Z and from Z to C. Okay. Let's check this. Yes, you can see that they find all the paths from C to A and from A to C, and here them. This is our graph. We can go from C to Z, from Z to B, from B to A, and they're done. So guys, I think that's all for this first video about graphs. If you like it, push like button, write comments, subscribe, and see you in the next video, the part 2 about graphs, where we will implement the BFS, DFS, and maybe some other functions. So, thanks for watching and bye.